Have you ever stopped to think about how your computer knows that an update it just downloaded is legit? I mean, how does it know it's actually from the software company and not some hacker? Well, the secret is something that works just like an old-school wax seal, but for the digital world. Today, we're going to pull back the curtain on Message Authentication Codes, or MACs.
Okay, so let's get right to it. The biggest problem in all of digital communication really boils down to one word: trust. When you get a message, an email, a file, whatever it is, how can you be 100% sure it came from who you think it came from? And maybe even more importantly, how do you know it wasn't messed with along the way? This is the exact challenge MACs were built to solve.
And here it is, the hero of our story, the Message Authentication Code. You can just think of it as a small, unique tag that gets attached to a message. It's basically a cryptographic checksum, and its whole job is to act as a seal of authenticity, proving that the message is the real deal. So how in the world does this digital wax seal actually work? Let's break down the core idea behind how these things create that critical bond of trust between a sender and a receiver.
The whole system, and this is really the key, it all hinges on one single thing: a shared secret key. This is a symmetric system, which just means that both the sender and the receiver have to have the exact same secret key before they even start talking. You can think of this key as the unique stamp they're going to press into that digital wax seal. The process is actually pretty slick, and it happens in 3 steps. First, the sender takes the message and their secret key, and they run it through a special algorithm to generate the MAC tag. That's like pressing the seal. Then they send the original message and this brand new tag over to the receiver. Finally, and this is the moment of truth, the receiver does the exact same calculation on their end using the message they got and their copy of the secret key. If the tag they just made matches the tag that was sent, boom, the seal is unbroken, the message is authentic.
All right, but like any security tool, a MAC has a really clear set of rules. It gives you some specific guarantees, and it's just as important to understand what it doesn't do. So let's, take a look at the fine print. So here are the 2 main promises a MAC makes. On the left, you've got message integrity. This means if even a single bit of that message gets flipped or changed in transit, the final tag won't match and the receiver knows something's wrong. It also gives you message authentication. It confirms the message came from someone who knows the secret handshake, who has the key. But look over on the right. A MAC does not give you something called nonrepudiation. See, because both the sender and the receiver have the exact same key, the sender could always turn around and say, "Hey, I didn't send that. The receiver must have made it themselves." You can't prove who sent it to a third party, like a judge.
So how do we actually build one of these MACs? I mean, what's the recipe? Well, this question led to a really interesting story of evolution, especially when it comes to using cryptographic hash functions to do the job. The first couple of ideas were, well, pretty straightforward. One approach was the secret prefix, where you just tack the key onto the front of the message and then hash the whole thing together. The other idea was the secret suffix. You guessed it, you just stick the key on the end and hash that. Seems simple enough, right? Yeah, well, it turns out that simple wasn't quite secure. Cryptographers are a clever bunch, and they pretty quickly found some subtle but serious flaws in both of these designs. With the secret prefix method, for example, an attacker could sometimes add their own data to the end of a message and calculate a perfectly valid new MAC without ever knowing the secret key. So, yeah, we needed a better way. And that better way is HMAC. This is the breakthrough. Instead of just slapping a key on the front or back, HMAC uses this really clever double wrapping process. To put it simply, it kind of mixes the key and message, hashes them, and then it mixes that result with the key again and hashes the whole thing a second time. This nested approach slammed the door shut on the vulnerabilities of the older designs. And this wasn't just some random idea. Back in 1996, a team of cryptographers, Belair, Canetti, and Kravchuk, formally laid out the HMAC construction. And their work was so solid, so robust, that today, decades later, it is still the gold standard and one of the absolute cornerstones of internet security. Okay, so this isn't just theory for a computer science class. MACs are out there, in the wild, working behind the scenes pretty much every minute of every day to keep your digital life secure. Every single time you see that little padlock in your web browser, that's HMAC doing its job as part of the system that secures your connection. But there are other flavors too. Some, like CBC-MAC, are built using different tools called block ciphers, and others, like the super-fast GMAC, are essential for securing things like the VPN you might be using for work right now. So you might be wondering, why use a MAC instead of a digital signature? Since signatures do give you that non-repudiation thing we talked about? The answer is one word: speed. Because MACs use those efficient symmetric key algorithms, they are way, way faster to calculate. And in a world of high-speed internet, that performance difference is absolutely everything.
And this need for speed is exactly why specialized versions like GMAC were invented. It's built from the ground up for high-throughput situations where you have to authenticate data at blistering speeds without slowing everything down. Just how fast are we talking? Well, GMACs can churn out these authentication tags at speeds of 10 gigabits per second. That is a mind-boggling amount of data being secured in real time, which makes it perfect for the heavy-duty hardware that runs our networks.
Okay, let's bring it all home. After all this, what's the final verdict? Why are message authentication codes so fundamentally important to our digital lives?
Here are the big takeaways. 1. MACs are our digital wax seals. They give us integrity and authentication. 2. Their real power comes from being fast and efficient, thanks to symmetric keys. 3. Standards like HMAC and GMAC are the invisible workhorses securing huge chunks of the internet. And finally, number 4, and this is the one to really remember. They create trust between two parties who share a secret, but they can't provide absolute proof to anyone on the outside.
And that leaves us with one last thing to think about. We're entering an age where AI can generate incredibly convincing, but totally fake content. In a world like that, the fundamental problem that MACs solve, proving a message's true origin, might just become the single most important security challenge we face. The only question is, will the tools that have protected us so far be enough for what's coming next?